Okay, so we've got a question here, and it's 7x squared minus 41x plus 54 is congruent with 0 mod 75. Now we need to find some solutions for x. Now, first problem we've got is this modulus 75. Now it's not a prime number, but the prime factors of 75, that will be equivalent to 5 times 5 times 3. That's our 3 prime factors. So what we're going to do, we're going to break this down into the modulus terms for each one of these, and let's see if we can get a solution. But the 5 times 5, we see that is a square. So if we put this in brackets here, that's equivalent to 5 squared. We can use something called Hensel's Lemma. So what that involves is, we'll try and solve this first mod 5, get some solutions for the modulus of 5, and then we'll go into some derivatives and stuff like that. So I'm going to show you how that's done. So first of all, we write this equation: 7x squared minus 41x plus 54 is congruent to 0, and then we do mod, and we just do the mod 5. We'll come to mod 3 in a minute. That's going to be the easier part. Okay, now this we can see is factorable. So 27 and 2 will be factors of 54. 2 7s are 14. So 27 and 14 is 41. So we write this down as 7x and x is congruent with 0 mod 5. Now we've got a 27 and 2, or 27 times 7 is not going to work, so the 27 is going to have to go here. And it looks like they're both going to be minus signs, because we've got a positive here and quite a low minus there, so that's minus 2. So now breaking this apart, we've now got x, so 7x is congruent with 27 mod 5, and we've got x is congruent with 2 mod 5. Okay, so 7x minus 27 puts 27 on the other side. That's how we get to here. Now we need to find these x's. So this one is quite simple. So this one is just x equals 2, and we write that as plus 5k. And then this one here, 7 times x is congruent with 27 mod 5. Well, 7 is congruent with 27 mod 5. So we just write down here x is 1. So now we write here for x is 1 plus, and then 5k. And that's important that we write it like that. Okay, so next thing what we need to do now is using each of these terms separately. I'm going to now denote these as x1 and x2. It's going to be important that we don't mix these two things up. So now what we'll do is we'll let this function here be f of x. So f of x equals 7x squared minus 41x plus 54. And then we're going to take the derivative of this as well, because it's going to come in useful for us. So f prime of x equals, well, that's going to be 14x minus 41. And now we evaluate the value of the function and the derivative at each of these points. So f of x1, so plugging in this value here, we're not going to worry about the infinite solutions, and same with this one. So this is all we're going to be interested in for now. Plugging 1 into here, we get 7 minus 41 plus 54. Well, minus 34 plus 54, that's minus 20. So that equals, sorry, plus 20. That's plus 20. Now f of x2. So plugging in 2 for here. So that's 28 minus 82 plus 54. Well, add all these up, we're just going to get 0. So that's that part taken care of. Now we're going to evaluate the derivative at each of these points. So f prime of x1. So plugging in 1 here, we get 14 minus 41. So that equals minus 37. And now we're going to take x2. That's going to be 28 because x is 2, so 28 minus 41. So that equals minus 13. Okay, now just to use this lemma, what we need to do now is just check a little condition here. The greatest common divisor of f prime of x1 and the modulus, which is 5, equals 1. And the same here, f prime of x2 and 5, that also equals 1. So, well, minus 37 and minus 13 are not divisors of 5, so these, check, they're good. Okay, so now what we're going to do, we've got a little formula which we can use here. So we're going to write this formula as, let's just take this off actually, we'll write h. H equals, you can use any letter, it doesn't have to be H, but I like to mix up my letters so I can see exactly where I am on my calculations. So H equals f of x, so in this case we'll do x1, divided by 5, so that's the modulus, and then we add f prime of x1 times k. Okay, what we've got to do now is simply, we've done all the calculations and check the condition, just plug these in and then we can see if we can find a value for k. So f of x1, that's going to be 20, so that's 20 over 5. F prime of x1 is minus 37, so this plus minus 37 will now become minus 37k. And then what we need for that, we need to solve for that modulus 5. So congruent with 0 mod 5. So now this leads us to 4 minus 37k is congruent to 0 mod 5. So how can we get this to go congruent to 0 mod 5? So we're a multiple of 5 with k here. Now the minus 37k, don't let that put you off. You can just plug in values for k as you wish. So 2 37s are 74. So minus 74 plus 4 is 70, which is congruent with 0 mod 5. So therefore k in this case equals 2. Okay, so that's that one. Now let's work on this one. So let's just put a line on here to keep these separate. So now we know our formula. We're going to write it as f of x2 over the 5 plus f prime, keep these separate, let's not get these mixed, f prime of x2 times k. Let's put a little nudge in there. Okay, f of x2 we know is 0, so that equals 0 over 5, which is going to be 0 something. And then f prime of x2k, that's minus 13, so minus 13k. So that's minus 13k here, and that's mod 5. So we need a value for k in there. So, well, if you plug in a 0, 0 is congruent with 0 mod 5, so therefore k equals 0. Okay, so we've got k is 2 for this one, and our original calculation for x1 was 1 plus 5k. So now what we can say is that x1 equals 1 plus 5 times 2, which is our k. Here we've got k is 2, and that is mod 25. So in case we had a big number there, we can just still break that down. For example, if k here was, let's say, 7, we'd have 1 plus 35, which is 36, in which case our k would be 11, still be 11. Or if k is 8, we'd have 1 plus 5 8 is 40, that'd be 41, in which case k would be 16. Oh, sorry, x1 would be 16. So therefore, x1 is 11. So same for this one. In this line of k for x2, it's 2 plus 5k. So let's write that down. x2 equals 2 plus 5k, and that's mod 25 as well. So therefore x2 equals 2. Okay, so now we've worked this out now for this part of our question, modulo 25. So I'm just going to put a little square around that. So we've got x1 equals 11 and x2 equals 2. Now we're going to need those for our next stage. I'm going to rub this off the board and then we're going to move on to the next stage. Okay, so we've got x1 equals 11 and x2 equals 2. Okay, so that's where we're up to so far. But now what we need to write down now, because it's for the 5 squared, we add this as plus 25k, and the same here. Okay, so that's taking care of the 25. Now we need to have a look at the 3. So we solve this now for the congruence modulo 3. So we got 7x squared minus 41x plus 54 with 0 mod 3. And then we factored it before. So we had 7x minus 27, x minus 2, congruent with 0 mod 3. So then we had to split that up into 2. So now we can say x is congruent with 2 mod 3. And so our x value here, we can say x is going to be 1. Sorry, x is going to be 2, sorry. So here x equals 2. And 7x minus 27. So now we say 7x is congruent with 27 mod 3. Now what can we multiply 7 by to get modulus of 27? Sorry, with congruent to 27 mod 3. Well, if x is 3, that's 21, which is congruent with 27 mod 3. So here we've got x equals 3. So if x equals 3 mod 3, we also have x equals 0. So we can change that to 0 and make our calculations a little bit easier. So if it's congruent with 0, don't let that make you feel uncomfortable, it's still good. It makes our calculations easier as well at the end. And then we need to put the infinite solutions down. So 0 plus 3k, 0 plus 3k. Now at this stage, I sometimes like to change these letters so we don't have the same values here. So I'm going to change these to n and m. So that's an n, and that'll be 3m. And we must also state that n, m and k are all integers. So we're always dealing with whole numbers in doing modulos and congruences. Okay, so now we've got this value here, this one here, this one here, this one here. So we'll call this x3, we call this x4. So let's write these up over here. So now x3 is 0 plus 3n, x4 is 2 plus 3m. Okay, so now let's work these out now using the Chinese remainder theorem. Let's rub this one off the board to give ourselves a bit of space. So I'm going to call these equations now letters. So this one will be A, this one will be B, call this one C, and this one D. So now what we need to do is do A with C and D. So A will go with this one and this one, and then the B will also go with C and D. So B will go with this one and this one. We don't have the A with the B, we don't have the C with the D, because their modulos are the same. Okay, let's deal with the A and C now. So A and C. So we take the first part of A, and now we're going to eliminate all these different letters here now. I'm just going to call this X. So X is congruent with 11 plus 25k, and that is also congruent with, now as we're dealing with C, we want to take congruent with 0 modulus 3. Okay, so now we just take this part and this part, and now we get 25k is congruent to minus 11 mod 3. So this 11 comes onto the other side, and now what we do is we find a value for k which is congruent with minus 11 mod 3. Well, minus 11 mod 3 will give us plus 1. So 25k is congruent to 1 mod 3. Now what value can we have for k? Well, 25 is congruent to 1 mod 3, so k equals 1. Okay, so now we have 1 mod 3. So now what we write is in here, x equals 11 plus 25 times 1 plus 3n. So instead of mod 3 we could have written here plus 3n. So let's write 1 plus 3n in here. Okay, now let's just factor this out and see what we got. We got 11, 25 times 1 is 25, and 25 times 3n is 75n. So therefore x equals 36 plus 75n. So now we've found one of our solutions, which is going to be x equals 36, and it's 75n. It's now mod 75, which is the answer we're looking for. Okay, now let's go A and D. Okay, so we've got x equals 11 plus 25k is congruent with D, which is 2 modulo 3. Okay, now just simplifying this off, we've got 25k is congruent with, subtract 11 on both sides, 2 minus 11 is minus 9, minus 9 is 0 in mod 3 language. So therefore k equals 0 plus 3n. So now we're going to factor in this k into our original part. So now x equals 11 plus 25 times 0 plus 3n. Okay, so now x equals 11, 25 times 0 is 0, plus 25 times 3n, that's plus 75n, and that is modulo 75. So there we go, got a second solution here. X is now 11. Okay, now going through the B's. So B and C. So B is now 2 plus 25k. So we've got x equals 2 plus 25k is congruent with 0 plus 3n. So 0 mod 3. Okay, so 25k now is now congruent to minus 2, if we bring that over the other side, which then gives us 1. So 25k is congruent to 1 mod 3. Okay, so we need a value of k, so now we can see that k here is 1. So 25 times 1 is 25. 25 is congruent with 1 mod 3. So k equals 1. So now plugging that into here, we need to put the 3n in there as well. So now we get x equals 2 plus, so 25 times 1 plus 3n. Okay, lots of numbers and patterns here to follow. It's very important to just concentrate on which ones you're going to get. One number in the wrong place and we're going to make a mistake. So you can see where the mistakes happen here. So 2 plus 25 times 1, which is 25, plus 75n. So that equals 27 plus 75n mod 75. So now we've got another solution. Okay, so that's B and C. So all that's left now is B and D. Okay. So x equals 2 plus 25k. So that is now congruent. Oh, okay. It's congruent now with D. So that's 2 plus 3m. So that's 2 mod 3. So if you subtract 2 on both sides, we get 25k is congruent with 0 mod 3. So therefore k equals 0. So now plugging that back into the 2 plus 25k. So x equals 2 plus 25 times 0. Now not forgetting the 3n here. 0 plus 3n. And 0 plus 3n in here. Okay, so x equals 2 plus 25 times 0. That's just 2 plus 75n. So there we go. So that's our 4 solutions. We've got x is 36, x is 11, x is 2, and x is 27.